We lecture on queue-size scaling in switch networks. Devavrat.
Thank you, Francois.
Can you fix the lights? Yes.
I would like to thank organizers for inviting me. And clearly, 3 years back, roughly 3.5 years back, it was March when I was here, and I have very clean memories of the place. I still remember the streets and the coffee shops. All right, so this talk is about designing scheduling algorithms or resource allocation policies for switch networks. The goal here is to design algorithms so that queue sizes are minimized on average if it's a nice stationary setting or long term in general. Equivalently, we'll try to minimize the delay or average delay. I'll go back and forth between queue sizes and average and delay for that reason. This is joint work with Neil Walton, who is at University of Amsterdam, and Yuan Zhang, my former student, now at Berkeley and on his way to Columbia. All right, so as the talk will progress, I'll make sure what I mean by switch networks and what I mean by queue size scaling. Switch networks at a high level are instances of the stochastic processing networks that many of us have been looking at. Its special instance, which is input queued switches, which I'll focus most of this talk on, has been with me since I started my PhD. It's more than 10 years now. It reflects on something. Since then, I've been looking at this question, and it is one of the reasons why Damon and I were looking at log-weighted scheduling algorithms, which the previous speaker, Philip, discussed. We ran against the wall, and some of the walls have been removed by Philip, which is great, but we just couldn't finish it. And in some sense, this is kind of anticlimactic. It solves part of the problem, but there are questions that remain. So I'll tell you what problem we have solved and what hopefully remains that will become clearer at the end of the talk and going forward. Okay, so let's start with queue size scaling. In this talk, I'm going to be interested in scaling in two forms, in like classical sense in terms of dependence with respect to the load of the system, and the second is the size of the system. So let's just quickly remind ourselves, like an MM1 queue, the delay scales like 1 over 1 minus rho, somewhat universal as we know. The scaling would be when rho goes to 1 from below. And really, it's this part that we are interested in. And it's this form that we are interested in. Now, if I have many queues in parallel stacked up like this, here I've just slowed down the time, but I have stacked queues in parallel. So of course, delay is going to increase by n because I have slowed down the time. Equivalently, queue size will also increase. Of course, for each individual queue size is not changing. It's effectively 1 over 1 minus rho, but then there are n of them. So total queue size is n over 1 minus rho. Okay. Now, one looks at this and says, well, aren't we doing something suboptimal, trivially suboptimal? That I've got total resources, which is amount unit, and I've got total load, which is total rho, which is less than 1. So maybe what I should do is I should try to pool my resources, and if I pool my resources, then effectively it looks like one single queue, and in that case my delay would be back to 1 over 1 minus rho, as if it's one queue. So even though I have many resources, as long as in this kind of setting, let's say every time a server becomes free, it's going to make sure that it provides its service or service token to a non-empty queue. It's going to be a nice world. So point here is that, well, if I restricted you not to sort of pool resources, then of course there will be limitation, and that will lead to poor delay. But if I did not have that limitation, then sort of I can do pretty well. Look, let's suppose that I did not have any such limitation. That is, I did not require you to split the resources, and in which case, if you did well, as in chose a sensible policy, you would get best performance. But if I asked you to do something not so sensible, that is, every time a server becomes free, chooses a queue at random and provides its service token. If queue is empty, the service token will go waste, otherwise queue will be served. In which case, again, we are back to the previous picture, and we'll have this kind of behavior. The point is that, well, if I have, even though resources may not be terribly constrained, but the policy is not done right, then we might have poor performance. So there are two reasons why sort of you might have certain performance. And the goal of this, at a high level, the quest one is after is like this, that I've got a generic resource constrained network. So think of this as, let's see if this is working. this one, yeah. Okay, so these are my, let's say, servers, and these are queues, and there are some constraints, and constraint determine which servers can serve which queues simultaneously. Okay. In the simplest example that I showed you of parallel queues, each server could serve only its own queue at a given point of time. In unconstrained setting, any server could serve any queue, and there may be everything in the middle. And the question is that depending on the constraints, how would the delay scaling look like? Maybe given the constraints are so nice that actually we could achieve this if we chose policy properly, or maybe constraints are so terrible that no matter what we do, it would have some somewhat more stringent performance. Okay. And the question is that depending on what constraints are, how the performance would behave. So now let's sort of, I'm going to spend some time defining a specific model of constraint queues, which is the input queued switch. Some of, or many of you have already seen it many times. Still, I'll go through slowly for the interest of others. And then we'll define the question, we'll define what the load is and define the sort of goal, and then sort of discuss the policy. Okay. Again, feel free to stop me anytime. So here is an example of two-port switch. It's like a traffic junction. I've got 2 input ports and 2 output ports. At each input port, there is traffic arriving exogenously. Traffic will be in form of packets. Packets are of unit sized. Okay. At each input port, there will be packets arriving for different outputs. So these is arriving for this one, and these are arriving for them. As shown in the picture, all packets are queued at the input side. And since packets will be queued separately for different outputs, so in this case, I have got total 4 queues. In general, if I had n ports, there will be n squared queues. So now the whole goal is to send packets from inputs to outputs as quickly as possible, because packets, when they're waiting here, that's when they're building up queue sizes or inducing the delays. Right, so what are the constraints? The constraints are the matching constraints. I'm assuming that system is operating in discrete time in nice synchronized fashion. That is, in a given time slot, each input port can transfer one packet from one of its queues to appropriate output. Okay. Each output can also receive one packet in a given time from one of the inputs. However, the constraint says that you can't send 2 different packets from the same input to from 2 different inputs to the output. For example, this is not allowed because I'm sending packet to this output from both of them. Okay, so this is not allowed. But what is allowed is this one, where I'm sending separate packets from inputs and outputs. And here is one example when this happens. Packets will go like this. Or here is another example. Packets will go like this. Now, sneakily, I'm introducing this matrix representation of the schedules or the actions. And effectively, they're saying that this is matching in a bipartite graph. So there is 2 inputs, 2 outputs. So I'll put these outputs here. And an edge between input and output effectively corresponds to this queue. Okay, and there are 4 queues, in general, n queues, n nodes left, n nodes right, n square queues. Okay, and the matching would be either these kind of parallel edges, or the cross, or the cross edges, which would be these 2 things. Okay, so the question of scheduling is effectively, I've got packets coming, they're sitting at input side. At each discrete time, I need to decide whether in this setting, whether I need to choose parallel edges or cross edges. And depending on which one I choose, the corresponding packets from inputs to output get transferred. Okay. Any questions about the basic model definition? I'm going to introduce a little bit of stochastics in a second, but before that. Okay. All right, so in general, it will be an n cross n switch. I'll restrict most of the talk for 2 cross 2 example. Okay, so here is a little bit of stochastics, and then there won't be much. So I'm going to assume that packets are arriving as per Poisson processes. They're independent. For example, at input 1 for output 2, packets are arriving at rate lambda 1 2, and that's as per Poisson process. And this is the number of packets waiting at input 1 for output 2, and that will be represented by these queue size matrix. Okay. Now, so I effectively defined the simple stochastic model for this input queue switch. Question is, we are interested in figuring out what is the best performance we can get or hope to get for average queue size scaling or average delay. And of course, we know that it should depend on load. So first question is, what is the load? And then what is the size? Okay, so just here is a precise definition of load. Let me read it out through an example. So let's suppose that in this case, this is the arrival rate matrix. So this is the rate at which packets are arriving at input 1 for output 1, and so on. Then a load in this case is computed as follows. Take the row sums, take the column sums, and take the max of that. Okay. In this case, it's 0.9. This says that total rate at which data is arriving at input 2 is 0.9. In a sense, it makes sense because look, from any input we can send at most one packet out, and total rate is 0.9. So in a simple single queue sense, this is the load. This is for the outputs, and again for that 0.7 should be at least that much of a load. What is nice is that despite matching constraints being the 1, this is the load, and that's because effectively these are my actions or resources that I have. I can take this matrix and split it in such a way that effectively 90% of the fraction of my resource I need to utilize. Okay, and this is because of this standard Birkhoff von Neumann result. Okay, so now that I have a model set up and I have defined load, question is, can we design scheduling policy? There is the one that chooses matchings each time depending on system state, maybe the history, so that the average delay scales like 1 over 1 minus rho. In the equivalent form here, the average queue size should scale like n over 1 minus rho. Okay, and this would be the ideal thing if we can do. Okay, and by scale, I'm going to forgive myself if I had few constants that are universally sitting there. Okay, any questions about the problem? Excellent. Okay, so let's just to get a sense that it's not that straightforward, let's look at a trivial policy. So here's a trivial policy, and the trivial policy is coming from a previous slide. That I have a rate matrix lambda. Let's say I told you that, or you learnt it, doesn't matter. And since I know that load is less than 1, I could decompose it like this. Okay, now this already suggests me a policy, right? Anyone wants to take a shot at it? It's a trivial policy. So let's say I know that I can serve this, all I need to do is make sure that I'm serving each queue at a rate that is higher than its arriving rate, right? I know that as per this decomposition, if I served 40% this and 50% this, I will be serving everybody at the edge. Of course, I don't want to do that. I have a slack of 10%. Maybe one way to divide that slack is uniformly. So let's say roughly 44.44% I'm going to serve this, and 55.55% I'll serve that. It's a nice, clean, uniform schedule. In which case, what will happen? Well, this is good because now we can stare at each queue and analyze it separately. It's effectively like a simple queue on its own, at least for the purpose of analyzing average queue size, and that would lead to total average queue size like n square over 1 minus rho, or delay like this. Okay. So clearly, this suggests that yeah, it's trivial policy. It will keep us, let's say, colloquially speaking, stable, but it will lead to poor delay. Okay, so we need to do something something clever. And let's see, why is this doing so badly? Well, it's not taking the queue sizes into account. So it's like that in trivial example that I had showed you. Like you were choosing a queue to serve at random, so you are not really utilizing your resources efficiently. So maybe one way to get over this is to try thinking about what are the precise queue sizes and take those things into account while serving. And this is what has been done for a very long time. And here is one very nice scheduling policy, max weight matching, originally proposed in Tashilas and Aframides in '92. And here is how it goes. I've got two schedules. For each one of them, I'm going to compute their weights. In this example, I'll compute weight as sum of the queue sizes. building upon previous talk, I could use a function of q size, for example, logs of these weights, and there will be a log weight. I'm not going to discuss that. Coming back to this example, if this guy has weight 2 plus 2, 4, this guy has weight 3 plus 4, 7. These are my two choices. I'm going to choose the one which has highest weight, and hence this will be the max weight. It's a nice policy. It has all sorts of nice properties. Most importantly, to begin with, it is stable. One does some analysis, and using standard bounds, one would find something like this. So I'm just rewriting it for the first time in a different way. All I'm saying is that I'm interested in scaling of rho going to 1, and I'm looking at this total q sizes on average multiplied by 1 minus rho. It's upper bounded by 4n square. This is what we get. This is the best optimized bound that I know of. Maybe if you know better, potentially you might shave off constants, but nothing more than that. And this is not good, right? Because this is effectively as bad or as good as the trivial policy we saw before. Okay. And now you look at this and you ask, well, is this true or is it not true? So one way to figure that out is to run some simulations. So let's run some simulations. So here's a plot where load is on x-axis. On y-axis, I'm plotting normalized total q size and normalized this way. It is the total q size divided by n. Okay, and this is plotted for different n's, and as you can see, they're effectively coinciding on each other, suggesting that this is the scaling with respect to expected q size. So total expected q size is scaling with respect to n and not larger than n. Okay?
But when you said, is this true or is it not true, what were you referring to?
That is, thank you. That is this not only upper bound, but it is a lower bound?
Say that again?
That not only this is an upper bound, which we know, is it also a lower bound?
Cannot do better.
Cannot do better. So, for example, cannot do better than n square over 8 or n square times any universal constant. Okay. And at least the simulation suggests that it is not true. That is, it is not a lower bound. In particular, it looks like the lower bound should be something like constant time n, not constant time n square. Okay. Let me replot it in a different way. That is, let me plot it this entire thing. And as n increases, of course, there is a little bit of drift here, but what you can see is it's settling up there. And I couldn't go farther than 32 because a Python on a Mac gives up after 32. Okay. So really sort of, also if you notice there's a constant half there, and you may want to remember half, it will show up at some point of time. Okay. So if I were to sit here and put a conjecture, here's the conjecture that for max weight algorithm, this is true. Okay, and at least Damon and I and many others have spent a huge amount of time trying to solve this. We have not solved it yet. Hopefully we will collectively. Instead of solving this problem, I'll solve an alternative version. Here is a different scheduling algorithm, not the max weight, and it has this fantastic performance. So let's just read it off. The same quantity of interest is bounded above by n, and of course if you look at this problem long enough, or not even long enough, 10 seconds, you will convince yourself that this is a reasonable lower bound for any algorithm. So what that means is that now we know existence of a policy, not necessarily the max weight, which is within factor 2 in this form. Any questions?
The centralized policy.
Yes, it's centralized. I don't even know if it's computationally efficient.
Do you have a guess for the asymptotics for a decentralized policy?
Okay, so let's say that in decentralization you allow me to exchange some information. Then I will go back to the max weight because there are many message passing like solutions we know for max weight implementation, and hence I would go back again and say this is the right answer. Again, I don't know anything of we don't know quite a bit, but we don't know this about max weight. Okay, so in the remaining 22 minutes, I'll spend time trying to explain the policy and why it is given intuition why it is working. Of course, we're going to stand on the shoulder of something, and I'll explain that. Okay, so let's just sort of spend one slide or two slides building a little bit of intuition. Why is the problem hard? So I'm borrowing a term, firing blanks from Frank when he visited. That's when sort of the term came around when he visited Stanford when I was starting my PhD. So let's suppose that here's one instance where these are the queue sizes. So this one has 2 packets that it want to send out here. This one has 2 packets that you want to send out here. Now here's one choice I can make. I can choose to serve these 2 guys, in which case I will serve 2 packets simultaneously, and that's as good as I can do. So it's pretty good in terms of short term. In a sense, it's greedy because I'm ignoring the queue size. All I'm asking is, are you empty or not empty? Okay, so in short term it does well, but there's a very nice counterexample by Anantharaman, Walrond, and McKeown, which shows that actually this type of policy is not going to work well. Okay, it is going to be unstable. The max weight in this setting would do something like this. That is, it will choose the long queue and it will starve this, and this is effectively it's firing the blank. Okay, so in long term it's going to do well, but there will be short term it will be a performance loss, and maybe this might be the reason why one loses performance. Okay, so maybe one compromise could be is do a convex combination of this. Well, I'm not going to do either, I'm going to do half-half. Okay. Now half-half is good because if I'm effectively half of the time I'm scheduling one, other half of the time I'm scheduling the other, it's not allowed as part of my model, because remember in part of my model I have to serve a packet fully, either this or that. But let's say for a second I allow you to relax constraint, that is in a given time slot you can, or not even time slot, at a given instance of the time you can serve data at a rate that is coming as a convex combination of all your possible actions. Okay. This is one convex combination, right? It's half-half. Okay. Then what can you do? In a sense, I'm making my discrete system a fluid system or a flow system. Okay. So for those who know, who remember or know the bandwidth sharing model, effectively I'm converting this switch network model to a bandwidth sharing model, where I've got 4 flows. This is flow 1, this is flow 2, then flow 3 and flow 4. There are 4 links here, link 1, link 2, link 3 and link 4. Each link has unit capacity, and all of these links are sharing these, the flows are sharing those links as I showed you. Okay. And for each flow at their ingress here, their demands are coming and they're sitting there. Okay. And I can serve them the way I like, in the sense of in a continuous sense. Okay. And I can sort of serve fractional amount. So that's my flow model. So at a high level, the idea is that here is my original system. I'm going to relax it into the flow system the way I described. Okay. For this flow system, which is a relaxed version, I'll try to find if there is a good policy, there is a good rate allocation, which will give me as good a performance as I want, or as claimed in my theorem. And then from there I will somehow peel off a matching, and while I'm peeling off those matchings, I'm not going to have much of an error. So it's like if you were coming from an optimization, they would say, well, isn't this what they would call rounding? Is you take an integer program, you relax it, write down a linear program or maybe whatever, and then solve it, get a fractional solution and round it off. And in the error process you may not incur too much of an error. And that's roughly what I want to do here. So the whole question is that, does this exist? Okay, and I'm going to sort of shamefully borrow a very nice result from literature. Okay, so any question about it at a high level plan? Okay, so here's a nice policy that was originally suggested by Laurent. Very nice result by Bonald and Alex, who is sitting here, which was for a specific class of file size distributions. And Zachary established a generalization of this, which is what we're going to rely on. Okay, so that policy roughly works like this. So I'm purposefully choosing a different notation now. These are those fluid queues. So effectively, the way you want to think of it is that I've got two systems working right now. One which is my original system, which is discrete time, and one which is this virtual system, which is a flow level system. Packets are arriving in a common fashion. They both get to the same. They both go to the same these two different systems. For flow level system, I'm going to maintain its own queue sizes, and at each time instance, I'm going to do a rate allocation. And the way I'm going to do rate allocation for flow ij, that is flow that is going from input I for output j, is effectively a ratio of some function, where that function is evaluated over in the denominator over the entire queue size matrix. In the numerator, it's queue size reduced by 1 in the ijth position. Okay. That function I'm going to skip for the time constraint, but I'll be happy to explain it offline. It's a beautiful choice of function, and that function leads to an assignment so that effectively my rate matrix has load less than 1, or put it other way, that it is lying in the convex hull of set of all actions. Okay. So it's a valid rate allocation. It's called store and forward allocation, and it has the following nice property. So let me parse this statement. So let me look at the flow level network, and let me look at it in stationarity, and look at the sum of the queue sizes, or sum of the jobs that are waiting in that flow level network. That is exactly same in distribution to the sum of the jobs that are waiting in the system in which I have effectively 2n independent MM1 queues. Okay, and what are those MM1 queues? Well, they're effectively it's a best possible thing. So look at this input 1. It has service rate 1 and arrival rate, which is sum of all the rates from all the external arrivals. That's one MM1 queue. And then there will be n here and there will be n here. Okay. So this is as good as it gets. Okay. And once you have this, you would immediately conclude that average queue size scales like this. So really, effectively, because of this policy, the whole scheduling constraint in this sense just disappears. Okay. There is factor 2 loss, as we can see, but up to that it just disappears. Okay. So this is fantastic. Yes.
The product form is a precise statement for a fixed n, is it?
Yes. It's precise. There's no approximation.
Arrivals, and here you have discrete.
Yes. So that's correct. So Zachary establishes this result for the setting in which we are looking at, where there is a unit size packet that is deterministic service and Poisson arrivals, and then it's exact. It's insensitive.
But what is n? Oh, it's insensitive.
It's a slotted time model, right?
Yes.
That's, I guess, his question.
No,
Well, so it's not slotted time. This is the relaxed model, right? So I need to go back to slotted time, and that's a result. So I would say it's not straightforward.
And would you just review briefly what is the relaxation?
Sure.
Just the key words that go with the relaxation.
Perfect. So, so in original system, we are required that system serves jobs every discrete time, and in a given time slot, you would either serve a packet fully or you would not serve the packet. Okay. So that's the original system. What is the relaxation? The relaxation is that now there is no notion of discrete time, it's continuous time, and at each time instance you can decide to serve jobs at a rate where a rate is not necessarily a matching vector, but it's a convex combination of matchings. Okay. All right, so now that this has happened, let's see how we will peel off matching out of it. So here just so here is, let's say, original system, and here is my virtual flow level system.
So you didn't explain what store and forward allocation is?
No, I have not. It's hidden in that phi function.
We don't need to know that for this.
No, thank you. All you need to know is that it's a pretty good allocation.
But it's building on the great edifice of product form stationary distribution.
That's correct. Yeah, I mean it's like it's bridging last 4 or 5 decades, which is good. Okay, so let's suppose in my relaxed system, at the end of one time unit, after choosing all sorts of rate allocation, maybe I might have changed 20 times in the middle. This is the effective rate allocation that I did at the end of one time. Okay. And this is a feasible solution. Now I'm going to, at the end of first time, I'm going to decide what should I do in my discrete system. What I want to do is this, right? I want to make sure that ideally I'm doing the same allocation, then I will have exactly same performance. The problem is that I cannot do same allocation because this is fractional, and I'm required to choose either 1 1 and 0 0 or 0 0s and 1 1s. Okay, so what I will do, which is the next best thing, is try to be as close to this as possible, but less than that. Okay. So that means that if I, at any point of time, I look at the cumulative services provided here, which will be no more than this, but it hopefully won't be too far from this. And if that is the case, then I've got a bound on discrepancies between queue size between two systems, and hopefully that discrepancy won't be too big, and then that's that. Okay, so in this case, I'm not able to do anything because these are all half-half, and anyone I chose, I will overshoot it. So I'm going to just choose 0 0. Okay. Now let's say at the end of, okay, and this is my lag, right? This minus this. Okay, now let's say at the end of in the second time slot, second time unit, this is the average service that I have provided. Okay, I will add it to this lag. So now the total lag is this much. Now I'll look at these lag metrics, and I'll see if I can peel off any matching out of this. That is, I can find entries where each of those entries form a matching, and those entries are greater than 1 or greater than or equal to 1. In this case, this is a simple situation, so I'm going to peel off this matching. I'll serve these two packets accordingly. They're gone, and now my lag is reduced, and this is it. Okay. And that's it. This is all I'm going to do. So at each point of time, I'm going to maintain my lag matrix. From that lag matrix, I'll try to peel off matchings. Okay, and as long as I can. If I can't, then I would do nothing. Any questions? Yeah.
The general case, can you peel off any matching, or is there a particular matching?
In general case, I would be able to peel off potentially many matchings. Which we choose is arbitrary. What would be nice is that if we had a way to think about which ones to choose, so that it would change performance, and I'll talk about that in a second. It's a great question. Okay, so here's some more example. This is no matching. Let's say if lag was like this, effectively what I'm doing is I'm giving a little more detail. The general way I'll think about it is I'll take the lag matrix and I'll try to come up with its convex combination. And if I have any matching with its weight higher than 1, I'll choose that. That's what I will do. Okay, and here's a simple lemma. It says that total lag, if I kept on doing like this, no matter how this was working, total lag will never more than n square. Okay, that is, if I look at the lag matrix and look at the row sums or column sums, some of those things will be never more than n square. Okay, and it's independent of, I mean, it could be as badly overloaded as possible, I don't care. Okay. And here's a simple proof, so I'll spend next 30 seconds explaining the proof. If you look at a doubly stochastic matrix, it decomposes into matchings. By Carathéodory's theorem, we know that the number of components cannot be more than d plus 1. Okay, here the dimension is effectively n square, so you can't have more than d plus 1 components. Now, if you had the row sums or column sums greater than n square, then one of them must have its coefficient in convex combination greater than 1, and then you are done. Okay. All right, so effectively that's the most of it. If you have caught on, then this is not all of it. There's a lot more details that are missing, because this is assuming all full matchings. You'll have to worry about sub-matchings and so on. And there is a way to deal with it. As long as your set of schedules are a monotone set, this will be fine. A variation of. Yes.
What if one of your entries is big and all the others are 0? You can't pack a matching into it.
That's exactly the point I was referring to. So, good. So there you will use the fact that matchings are a monotone set, and a monotone set will allow you to establish that. I'm happy to talk to you offline. It's more than illustrations. Excellent. So I think I have effectively explained you this entire proof. That is, you start with the original system, get the ideal or flow system, gives you this fantastic allocation. Now we have added total of n square at worst, and that will give you this scaling. Okay. Now, since we are interested in rho going to 1, and there is no rho no dependence of rho here, this effectively washes away. Okay. Now, if I had rho and 1 minus rho in such a way which is let's say a function of n, that is 1 over 1 minus rho is larger than n square, which means that these two terms are comparable, again the same result will hold. But let's say rho is going to 1, or 1 over 1 minus rho is going to 1 at much slower rate compared to the n square, then of course this is not the best result. Okay, I'll come to that in a second. Let me quickly mention that how this would naturally extend to, yeah.
Yes, originally when you had the upper bound, I thought you meant it to be uniform over n and rho.
Correct.
But if you're going to take n going to infinity, rho going to infinity, and so on, in what sense did you mean that inequality?
I mean it in precisely the way I wrote the theorem. So let's go back to that theorem for a second.
So first you take the limit in rho, then in n, or?
Sorry about that.
For all n.
That's correct. In some sense, this is what give you, if you were to do diffusion approximation or heavy traffic, this is what it will give you. Because it won't allow you to differentiate between the simultaneous scaling. Yes?
Could you say a few words on how the psi function is used in the collection of matchings?
No, it's not at all used.
Sorry?
It's not at all used. It's independent. So it's a pure emulation result, which would work for any policy. So you could use, tomorrow you could go and say, I'm going to get better than student forward policy, okay, which for example I think Mike will talk about in his open problem. And if you had that policy, I would use that and rip it off. I mean,
It's not linked to that.
yeah. Okay, because of course we have nice MM1 queues, as you would expect, this would get a pretty good tail behavior. So there's a result by Sasha Stoliar which establishes large deviation exponent optimality in this sense for max weight algorithms. what this implicitly does is actually it characterizes it, and it says that it's effectively like as if it's a single queue. Okay. How would this extend to a general network? In 1 minute. In general, if I had n queues, some action set that would determine how the queues are allowed to choose. Here the action set was constrained by matchings. In general, you could have, let's say, independent set, which was what Philip's example was. So depending on that action set, you will have something like this. You've got, these are different actions, discrete actions. This is in some sense space of all admissible loads or arrivals. And let's say for admissibility or servability or stability, your rate vector must lie inside. In sense, each face is a virtual resource, and for each face we could define a load, which is rho. In the case of input queued switch, virtual resources are very clearly defined. They are input ports and output ports, okay, and that's where their rows showed up. In this setting, it will show up exactly like that. It's 1 over 2 times 1 minus rho j, where j for each virtual resource, and then there will be a constant that is coming because of the way we did emulation, and that constant would depend on, of course, the convex set, in particular the dimension of that. Okay, so this is precisely the dimension plus 1 of that. Okay, and again, it would have pretty good tail behavior. All right, I think I have still 2 more minutes. Okay, so in last 2 minutes, I'll just close the discussion on the simultaneous scaling between rho and n and what remains open. Okay, so I'm going to do somewhat unusual plotting. These are 2 scalings. This is scaling with respect to size. This is scaling with respect to 1 over load, or gap 1 over 1 minus rho. When they're scaling in the same way, that is 1 minus rho is equal to n, okay, universal constants forgotten, then so that's the line. This is a situation where n is much larger than that, in which case, of course, my results are not telling much. Okay, and the best one can get is a batching policy, which would be 1 over 1 minus rho square. This is what we know. Okay. In this case, which is pertinent to this talk, let me just quickly say, in this region, which is given by this is the best we can get. Okay. For max weight, as I had told you earlier, this is what is the proven so far. Of course, I would like to believe that this is true across, okay, but we don't know that. And here is a small progress we have made that applies for this region. So we have shaved off factor n, but there is still square root of n lurking. Okay. And again, we don't believe that this square root of n should be there, but that's that. All right, and here are the sort of 2 open problems, and I think I'll end the talk here.
Questions?
Yeah.
Can you explain how this connects with the work that Philip discussed about the logarithmic weights?
Sure. So the policy has nothing to do with it, but as a max weight, the basic max weight policy that I described, which tries to choose schedules by weighing their actions with as a just queue size. If instead of I weigh their actions by queue size, instead I weigh them by as a function of queue size, then I've got f max weight, let's say, schedule. If that f is log, or log of 1 plus x, then it would be a log weighted schedule. The simulations of Damon that Philip is referring to were for that log weighted or log max weighted network topology, which were actually just 4 nodes, 1 in the middle and 3 around. It was star It's like a very miniature version of independent set model.
So the question is why the log? That was the question.
Okay, good. Why did we spend sort of, let's say, 2.5 years of our lives, right, and a few travels across the continent? Looking for white chalk. Yeah, actually, yeah, yellow will work too. Okay, so. Oh, thank you. Okay, so initially we started with this thing called max weight or alpha max weight, as Philip referred, where the function was x to power alpha. Okay, then we spent time studying this policy. In particular, we tried studying this policy under critical fluid model, which comes up as a part of the heavy traffic. And there the idea was that, well, let's take alpha going to 0, then x to power alpha would look something like, okay, this is exact. Which is effectively 1 plus alpha log x. Okay. And then this guy was doing pretty well in terms of when we looked at its in context of switches, an input queued switch, the model I discussed in detail. There, this collapsed space would be effectively full, which means that you would not be touching the boundaries too often, which would be effectively least firing the blanks. And so that means that maybe we should go for this kind of limit. Well, how do you study limit? Let's do some expansion and see what happens. It looked like it is this guy that matters, plus 1. And then, of course, this is not exactly log weighted. It's first you look at maximum size and then you break ties using log weight. Spend some time studying it, and it is complicated. This was actually stochastic networks in 2006, right? It's Urbana. It was 2006, right? Yeah. Anyway, so and we were sitting in this hotel opposite CSL, where we realized if you look at just log weight and look at its, let's assume for a second all theorems go through, then its induced collapsed state space would be full too. Okay. And so then we say, well, let's go with that. And so we effectively almost established that. But after that, as Philip pointed out, just too many problems.
So you're doing scheduling looking at the queue lengths. Does it make sense to also forecast what you expect to see in the queue depending on the rates in the near future and use that in coming up with schedules?
So I think if I remember correctly, one of a student then in North Columbia, Siamak Mollemi, he tried to look at some such aspects using dynamic programming. And what he could show is that there was kind of improvement, but the improvement was very minimal. In some sense, I would expect that, okay, after these many years, maybe I would expect that all max weights, all reasonable max weights would be within constant factor of each other. So you'll get better constant factor, but nothing more.
So this is a sort of vague question, trying to understand what the point about the set S.
Yes.
So when you consider a generic network, then the set S will somehow describe the admissible region.
Yes.
Now, in the input queued switch, you've got a specific structure that lets you read off from the set S what N is.
Yes.
Now, I just wondered when you move to the generic case, you've got S. But
Yes.
Is it obvious? I mean, there's presumably a class of S where an N makes sense, but,
Yes.
but might it make sense in general?
Excellent point. So let's take a very simple alternative model. Again, bipartite graph, but constraints are not matchings. There is not on edges, but on vertices. There is the independent set model. So now, in some sense, each, let's say, because previously I had a node constraint, so nodes were determining my number. Now it's the edges that are determining my number. and that's how it would change. So in some sense, there it would be you would be better off not doing this, because there's sort of just you just have too many virtual resources compared to the number of queues.
Sort of related to a question that was asked before. A question that comes into my mind is, why is the top problem interesting? And I think I know the answer to that, that max weight is just important. It's the sort of baseline, right? It's the default, it's something or other. But you've talked about a scheme which is extremely complicated to implement, the Bonal-Poutier-Zachary scheme for getting the product form in the relaxed system and then round it off and blah, blah, blah. And it achieves the bound Cn.
Yes.
So who cares whether max weight achieves? What's the answer to that?
I think the answer is exactly in your comment, that it is pretty complicated. I don't even know it's polynomial time, because computing that function requires me to compute a partition function of.
But an alternate form of this top problem would show that max weight does this, which is be a vastly simpler thing than your complicated one. But in other words, give me something else as simple as max weight.
Sure.
That accomplishes this. That would be another form of the problem.
Sure. Yeah. Okay.
Any other question?
Yep.
Is the fluid, I mean, not the fluid, the Poisson arrivals, but in discrete packet sizes, but the fractional version of a max weight policy clearly doesn't have a product form, I presume. But is that something one recognizes?
So I think
in the case where it's equal sharing.
So let's say let's forget max weight and let's say proportional fair.
Yeah.
Okay, proportional fair would apply pretty well. Why not use proportional fair? Let's conjecture based on Kang, Kelly, Lee, Williams that the way they had the product form there would hold here, then all of these results will be fine.
Well, why do you want product form? No, that's where you know the Q size won't.
Sure, and that allows me to evaluate things. Otherwise, how would I evaluate it? In some sense, that's a problem with max weight, right? We just can't evaluate.
But that's implementable. I mean, sorry, that was the point of the question.
Yes, of course.
Any more questions? So let's thank the two speakers of this morning.